Welcome back to the playlist on alkene additions in organic chemistry. In this video, we're going to discuss a very useful reaction known as oxymercuration demercuration. Now, in the name of this, you see that it's probably going to involve mercury. And in fact, mercury is one of the driving forces for why this reaction is so useful. So to get an understanding why this reaction is incredibly useful, let's take a look at two different reactions here. The second one is actually going to be oxymercuration, demercuration, but the first one is when we have simple hydration of an alkene with H3O+. So normally when we did most of our hydration of alkenes, we just did a simple Markovnikov addition of OH to the more substituted position on the alkene, which is right here. And you see that one of the possible products, and I say possible products, is with the OH group in that position. But as you saw from the video on the hydration reactions, if we had the capacity for a carbocation rearrangement, then we can get an alternative product where the OH is actually in a completely different position due to either a hydride or a methyl shift. So I'm going to breeze through this mechanism pretty quickly, but just to show you essentially why we get two separate products. Hopefully you can rationalize why we get this simple one without the rearrangement. But essentially, if you want to look at the rearrangement, the pi bond here can act as a base. It can deprotonate the hydronium, leaving a carbocation right here, which is the more substituted position over this one right here. So it adds the carbocation to this one. But you have the capacity to turn a secondary carbocation into a tertiary one right here, which is significantly more favored. And so this hydride right here will shift over to the carbocation, which also moves the carbocation over to this position, making it tertiary and significantly more stable. And once that occurs, then water can attack there. You get a subsequent proton transfer to remove the extra proton, and you end up with the OH in this position. So one of the problems with hydration of an alkene is that if you have the possibility for a rearrangement, you can get at least two products, and that's not really good. So we'd like a way to avoid the production of multiple products and get one specifically. So let's take a look once again at the same compound that normally would have the capacity for a carbocation rearrangement if you do a reaction that doesn't really work well. Well, there actually is a set of reagents that you can use here, and when you do these reagents, it's termed oxymercuration, demercuration, and when you do this type of reaction, you actually only get the OH added at the more substituted position. So this is actually the only product that you get. So in molecules or alkenes that would normally have the capacity, this becomes an incredibly useful reaction because it avoids any unwanted side products for the most part. Okay, so we're going to take a look at how to do this. I just want to very briefly go over what the reagents are. We're going to come back to these products in just a minute, or these practice problems, that is. But the reagents is a two-step process. Number one, you're going to use something called mercuric acetate, and we're going to go over what that is in just a minute, and then water. And the second step, you're going to do a reduction using sodium borohydride, and we'll also look at that too. So what exactly is mercuric acetate? Well, normally when you see mercuric acetate, it's written in the above or below the arrow like this. You see Hg, which is the symbol for mercury. It's actually in the 2+ oxidation state. And then you also have two acetoxy groups. So an acetoxy group is basically whenever you have this acetate essentially, but the oxygen right here is actually bound to something else right here, and that could be a number of things. In this case, that's actually this mercury 2+ cation, or the mercuric cation. So a lot of times they'll even expand the molecule to look like this, mercuric acetate, but if you're looking at the complete organic structure with the mercury, it actually looks like this. Although normally when we're just doing the simple reaction predict the products, we just write this. Okay, so to understand why you only get the desired product, this one, let's look at the mechanism because that's going to help us understand it. And if you don't want to see the mechanism, you can skip ahead to where we do practice problems with this type of reaction. Okay, so this reaction of oxymercuration, demercuration is only a Markovnikov addition. You're not going to get any anti-Markovnikov addition, which means that we are always going to add the OH to this more substituted position right here. So this has two hydrogens, right? has 2 hydrogens, so that's the least substituted. This is a whole carbon chain over here, so we're going to add to that side on the right. So here's what's going to happen. Initially, when we have this mercuric acetate, we put it in solution with the alkene. Essentially what's going to happen is one of these acetoxy groups is actually just going to spontaneously leave. And so that's going to leave you with this species right here. This is actually the active species. Now notice here the mercury is essentially neutral because the 2+ charges are essentially canceled out due to the negative charges each of these acetoxy groups. Okay, so it's overall neutral. When the one acetoxy group leaves, mercury actually has a +1 charge, and that's extremely electrophilic, and that's actually what the pi bond attacks. Let's look at what happens. So in step 1, the pi bond is going to come out and actually attack the mercury because it has a positive charge. Now, the mercury essentially becomes bonded to the least substituted position initially, but something very quickly happens after it attacks. Notice that we would normally get a carbocation right here, and we do. And if we used hydration of an alkene, then we'd actually get this hydride right here to shift over. But instantaneously, once mercury is attacked and you generate this cation, there's actually a set of electrons on the mercury. They're going to come and nucleophilically attack that carbocation, and so you get this mercury 3-membered bridge right here. That's pretty covalent in character. Okay, what that does is it generates a pretty decently sized partial positive charge on this carbon right here. Okay, and it turns out that's actually what your nucleophile is going to attack. Now, normally, if we look at most of these reactions that I have down here, I simply have the nucleophile as water because that is the most common. However, the nice thing about this type of reactions is, say, if you wanted to add, instead of a hydroxyl group, if you wanted to add, say, a methoxy group, you can do that. So I have this OH here bound to an R. The R could be a number of things. If the R is a hydrogen, then you just simply have water as your nucleophile. If your R is CH3, then you have methanol. If you have R as CH2CH3, it's ethanol, and so forth, and you can add other carbon chains as well. But the mechanism is going to be identical. The specific nucleophile is the oxygen. So here's what's going to happen. And if it makes you feel any better, imagine this R as just a hydrogen. Okay? So it'd be water in that case. Here, the oxygen is going to attack that partial positive, and that's going to free up this mercury. It's just going to sort of swing up on here. And now what you have is you have this ROH. This actually has a positive charge. I neglected to draw that earlier. Has a positive charge. So now another ROH, if you'd like this as water, is going to come over here and just deprotonate that to neutralize that group. And so now effectively what you have is this OR. Again, if it makes you feel better, just consider that a hydrogen, in which case it'd be an alcohol attached. Okay. The last step is our reduction step. This is our second step that you see. That's where we use sodium borohydride. The sodium is just a spectator cation. It doesn't really play any role. But now what's going to happen is one of these hydrides from BH4. So if you look at BH4, overall that has a negative charge. And boron doesn't really like to have an overall negative charge. So the hydride will just leave, and it will attack this carbon, causing loss of the of mercuric monoacetate, okay? And so then you're just left with this right here. And if you thought about it like this hydride that left is attached to that carbon. And if you think about this R group as being hydrogen, then your compound that you get is just this, which is exactly what we wanted if you go back up here, okay? That's actually the product that we got, and that's the only one we wanted. So the nice thing about using this oxymercuration, demercuration, is because this mercury actually forms a bond with the carbon that had the positive charge, as shown right there, you avoid a carbocation rearrangement because that's not favorable in this case. And so then when the nucleophile attacks the more substituted position, then you only get the alcohol or whatever group you attach at that position, which is very good. Okay, so again, the best way to get a handle at this is just to jump into some problems. So these are the oxymercuration, demercuration practice problems. So the nice thing about this type of reaction is whatever your nucleophile that you're using, in this case it's water, you more or less only have to really worry about that functional group going on the more substituted side. Therefore, it is a Markovnikov addition. The only other problem with this type of reaction, though, is that Unlike some of the other reactions where you can get syn additions or it's purely anti-addition, you actually get a mixture of syn and anti. And so because of that, you actually can get a mixture of stereoisomers with some percentage of each of them. And so you do get a mixture of stereoisomers. That's the only problem with this. So if you know you're making a compound that doesn't have any stereoisomers, meaning it's going to be achiral, then you're in luck. But if you're actually making a chiral compound, then you're probably going to want to use a more enantioselective technique. Okay, so in general, we're just going to add the nucleophile to the more substituted. So in that case, that's a hydroxyl group. And so that's our product right there. Notice that our OH group, which came from water, is added to the more substituted position. And that's all there is to oxymercuration, demercuration. You don't have to worry about really anything else. This was one of those compounds that we looked at that had a hydride here. And in the case of a carbocation that formed, it would do a hydride shift and you get a mixture. But the nice thing here is whenever you do oxymercuration, demercuration, you're only going to get that OH group right here at the more substituted position. And we sort of already looked at the mechanism of that. So notice Markovnikov addition at the more substituted position and no carbocation rearrangement. Okay. Here's another one. This is one case where, again, we would normally have, if we used hydration of an alkene, for example, we would generate a carbocation right there at that carbon. Then the hydride would shift over and we'd get a mixture of products. But once again, the nice thing about doing oxymercuration, demercuration is that we don't have to worry about those rearrangements. And so we only get the hydroxyl at the more substituted position, which happens to be this position right there. So hopefully that makes sense. Here's another thing to just kind of test to see what you've learned so far. Now we'd like to do oxymercuration, demercuration on benzene, but as we've seen in some of the other videos, whenever we're trying to do reactions on benzene, benzene does have double bonds, right? Double bond there, there, there. But benzene has a type of resonance that we call aromaticity, and that drastically lowers the energy of the molecule and drastically increases the stability to the extent that it will not do oxymercuration, demercuration, since if we do it on benzene or any other aromatic compound, we essentially get no reaction. Okay, there are ways to hydroxylate benzene, but they are a lot more complicated, and those are typically covered in Organic Chem 2 a long time from now. Okay, so here's another alkene, but this case we're going to attach a different group. So remember how I said in the mechanism we had this little thing I showed where you had some R group and then that was bound to O and H. And I said if it was water, then certainly if it was water, then that R group was a hydrogen. If it was methanol, then that R group was a methyl group and so forth. So what we can do is actually use different R groups to essentially attach different groups. If the R group is not a hydrogen, then the functional group you're actually making is an ether. Okay, so actually the OH is right here. That's our OH. So what would actually be our R group that we're adding? Well, it's essentially all this over here. Okay, that's what we're adding instead of a hydrogen. So we're not making an alcohol. So what do I do is, well, I'm going to just draw the skeleton. Okay, and then at least the oxygen, which is the actual nucleophile with that lone pair, is going to be what adds to the more substituted side. But instead of just being a hydrogen over here, it's actually going to be 1, 2 carbons, so 1, 2, and then a benzene group on that. So that's actually one way you can make an ether. So we've actually made an ether here. That's what this functional group right there is. Unfortunately, notice that this carbon is actually a chiral carbon. But again, the problem with this type of reaction is there's a loss of stereochemistry in terms of the selectivity. So you would actually get this plus the enantiomer that goes with it, and that can be a problem. So, but if you're doing any kind of reaction that's it's no possibility of generating a chiral center, and you would get a rearrangement, then this is the reaction that you would do. Okay. So hopefully this discussion of oxymercuration, demercuration made sense. See you in the next video.